General relativity, step by step. Last time I was observing that if you compared the total density of the universe to this quantity here, 3h squared over 8 pi g, which I called rho critical, then the comparison tells you whether the overall curvature of the universe is sphere-like or saddle-like or flat. You don't normally consider the densities, the various densities of the different components of the universe. You normally consider omega. Let me write that out again. I'll pinch in a bit. You normally consider. I'll do it even more. You normally consider omega I, which is the density of I over rho critical. So you've got omega radiation, you've got omega m for matter, and I guess you've got the vacuum energy there. And so the comparison now becomes omega r plus omega m plus omega of the vacuum, compared to versus, I guess, 1, rather than messing around with Hubble constants and so forth. Okay, so what are the values of these things? Well, matter turns out to have a non-dimensional density of about 0.3, plus or minus a few percent, 0.003. It's quite well determined. That's 0.7 plus or minus. It's a little bit higher as an error, and the radiation is 5 times 10 to the minus 5. And so we can see that the two terms that dominated this one and this one, the matter and the vacuum energy, this one contributes a small but, well, a negligible term. Certainly in the current epoch, it would have contributed a lot more in the early universe. Interestingly enough, this term dominates here, the vacuum energy dominates, which is an interesting observation. It's possible to split the matter up into two bits. We can talk about it being composed of omega B for baryonic and only omega D for dark matter. So that's baryons equals atoms, I guess. And this one here is dark matter of unknown composition. And it turns out that that's about 0.25 and that's about 0.05. So they total 0.5. So they total 0.3 as they should do. So we can see that what we think of as matter, or luminous matter, I guess, matter that we can observe and that is interesting to us, things like planets and stars and stuff, that actually contributes only a very, very small amount compared to the other terms in our equation. And indeed, it turns out that only a very small proportion of this is actually in stars. The rest of it is in nebulas and stuff like that, simply because they've got a much higher volume than the stars have. So what we think of as astronomy is a very minor component of the cosmos. A couple more bits of notation that we get are, well, you're normally interested in the deficit. So what you do is you say that omega m plus omega r plus omega vacuum is approximately equal to 1. And what you normally do is you specify that alpha should be capital R for radiation plus omega for the vacuum equals 1 plus k upon h squared of t. Sometimes you see it with an a down there, but I'm defining it to be 1 here. So this is a definition of this. Def defines k here. And of course, if little k equals 0, then that tells us that the universe is flat. Okay, I'm going to stop there. Stop.